Welcome everyone to my completion seminar, and today I'll be talking to you about the k-Steiner tree problems. Okay, so first I'll begin with a little bit of motivation. I just want to point out that networks are very important and we rely on them day to day. So I'm sure that many of you has used some sort of network that I've listed here. So whether you say some sort of transportation network to get here, if you're on Zoom, you're relying on some sort of communication network. And obviously, utility networks are very important as well. So, and some of these networks can be very expensive. So an example I'm going to give you is the submarine cable network. So there's a paper which covered the submarine cable networks. And one such example cost $95 million. And it spanned a distance of 1,700 kilometers long. So these networks can be very expensive. So these networks are ubiquitous, and also they can be very expensive. So it's crucial that we make them efficient as well as reliable. So this leads us to the network design problems. And two examples I've given here are the minimum spanning tree problem and the traveling salesman problem, which some of you will be familiar with. So the first example, well, I'll go through the minimum spanning tree problem because it's very relevant to our problem that we'll be looking at. So the minimum spanning tree problem. So in the minimum spanning tree problem, you're given a set of points in the plane, and your aim is to find a network that interconnecting those given set of points that has the shortest total length. And it can be solved in polynomial time. So for example, Kruskal's algorithm is able to solve the minimum spanning tree problem. So an example I've given here, it's a very simple example where you have three vertices in the plane. And this is an example of a minimum spanning tree. So it's the shortest way of connecting these set of points. So just one thing to note is that a minimum spanning tree will not only minimize the total length of a network, but also minimize the length of the longest edge of a network. So I'll come back to that later. So next we'll talk about the minimum Steiner tree problem. So in the minimum Steiner tree problem, it's very similar to the minimum spanning tree problem, except that you're allowed to introduce additional vertices, which are called Steiner points. And you do that so that you can reduce the total cost of a network. And the vertices that are initially given in the problem we'll refer to as terminals, just to distinguish between the two types of vertices that we have. So this makes the problem NP hard. Below, we have two examples of minimum Steiner trees. So we have the same three terminals that we had before, except on the left, we have an example of a minimum Steiner tree that's minimizing the total length of a network. So the sum of the length of these edges is the shortest possible. And on the right, instead, you're minimizing the length of the longest edge. So you can see that the geometry is quite different depending on the type of cost function you're looking at. Here you have these nice 120-degree angles. And here instead, S, which is a Steiner point, will be at the center of the circle going through the 3 points. Okay, so what are the actual Steiner points? So as I've mentioned, the Steiner points, you use them to reduce the cost of a network, but they themselves can be quite expensive. So I'll go back to that previous example where I looked at the submarine cable networks. So this is an example of a submarine cable network here. And these green dots you can think of as the Steiner points. And at each of these Steiner points, you need to have what is known as a branching unit. So this hunk of metal, and they can be quite expensive. So it's estimated to be around $2 million. And I believe that's US dollars, so it's more expensive than Australian dollars. So while they can make the network more efficient, they also can make it more expensive. So what are we going to do? This motivates the k-Steiner tree problem, where it's exactly the same as the minimum Steiner tree problem, except we limit the number of Steiner points to some integer k. So for example, this is an example of a minimum Steiner tree. So this is the shortest network connecting these four terminals A, B, C, and D. So it's using 2 degree 3 Steiner points currently. But once you limit the number of Steiner points to, let's say, 1, then you end up with a single degree 4 Steiner point instead. So just to formally define the problem, so we're given a set of terminals, so n terminals in the plane, and we're given some non-negative integer k. And our aim is to find a connected network. So you can go from any vertex to any other vertex. It's spanning n, so it's connecting all the n given points, and you're using at most k-Steiner points so that you minimize the total cost function. And we haven't chosen the cost function yet, but from the previous examples, I think you have an idea as to what they will be. So the first cost function we're going to look at is the sum of the length of its edges. And if you do this, the problem is NP hard for general k for this cost function. And currently there are no exact algorithms that can solve this problem in practice. So that was one of our main aims, is to create an algorithm which can solve this in practice. Okay. So we'll talk a little bit about the Steiner points. So in a minimum Steiner tree, when you allow a limited number of Steiner points, you'll only get Steiner points of degree 3. Whereas once you restrict the number of Steiner points, you may also end up with Steiner points of degree 4. And just the thing to point out is with degree 3 Steiner points, they have this nice property where the angle between the adjacent edges will always be 120 degrees. Otherwise, it won't be optimal. So they'll have these nice 120 degree angles. Whereas for degree 4 Steiner points, you always have 2 pairs of collinear edges. So for example, AS3 and S3C would be collinear, and the other pair would be S3D and BS3. So you can think of as 3 collinear points down here and 3 collinear points down here. Otherwise, it cannot be optimal. And the reason why you only get, degree 3 Steiner points in the unrestricted problem is because whenever you have a degree 4 Steiner point, you can always introduce another Steiner point to further reduce the length of a network. But if you have a restriction on the number of Steiner points, you might not be able to do this. So you could potentially get degree 4 Steiner points as well. Okay, so now we need to define a few more things before we get to the algorithm. So we call the underlying graph structure of a tree to be its topology. And if every terminal has degree 1, then it's called a full Steiner topology. So for a Steiner tree, a full component where every terminal has degree 1 will be referred to as a full Steiner tree or an FST. So I've shown 2 examples of FSTs here. So one has 2 degree 3 Steiner points, S1 and S2. This one has a single degree 4 Steiner point. But they're both FSTs because every terminal, which I've denoted by these black squares as opposed to these open disks, which are these Steiner points. So every terminal has degree 1, and that's why it's an FST, regardless of the number of Steiner points. So why do we want to talk about these FSTs? It's because every Steiner tree can be partitioned into these FSTs. So this is an example of a Steiner tree, and we've divided into these 3 different FSTs, which I've shown in 3 different colors, which I hope you can all see. You have 3 different FSTs, F1, F2, and F3 here. And they're all FSTs because within those FSTs, every terminal has a degree of 1. Okay, so now, so we want to address the restricted problem where we limit the number of Steiner points to some number k, but we're first going to go back to the minimum Steiner tree problem where we're allowed to have an unlimited number of Steiner points. So there's an exact algorithm called k-Steiner, which can solve the minimum Steiner tree problem, and it's very efficient. So I've provided some numbers here just to show that, just to convince you that it's true. So if there's an instance with 10,000 terminals, it can solve it in less than 500 seconds. And there's been a recent result that has shown that it can solve instances up to 1 million terminals. So it's very quick. So we are going to base our algorithm on this k-Steiner algorithm, which can solve the minimum Steiner tree problem. Okay, so the k-Steiner algorithm consists of two main phases, the generation phase and the concatenation phase. And in the first phase, the generation phase, our aim is to generate a set of FSTs, which contains the FSTs of at least one optimal solution. Then in the concatenation phase, our aim is to find a subset of those FSTs that actually give you the optimal solution. Okay, so I'll go into a little bit of detail about the generation phase. So we want to generate each of those individual FSTs. So to do that, we're going to deal with these structures known as branches. And with branches, you can think of as partial or unfinished FSTs. They're the building blocks for the FSTs. So here's an example of a branch. So it looks similar to an FST that I've shown you, except it has a ray coming out of a vertex. So I've shown a single ray here, but in fact, you're dealing with a range of rays, and these kind of show you the direction in which you can merge these branches to generate these FSTs. So I know it might not be very clear, so we'll go through an example just to get an idea. So remember that in the k-Steiner algorithm, we only have 3 Steiner points. So we have these processes called the double merge, which creates these 3 Steiner points. So initially, you're going to begin with these little branches at terminals A and D, and you'll perform a double merge. So what does a double merge do? It combines these 2 branches. It generates a single 3 Steiner point and a range of rays, which shows where it can merge next. So we've done that, and it turns out that within this range of rays, you have a suitable ray. That means that you can merge with this branch coming out of terminal C. So in the next step, we're going to double merge again. And again, we create a 3 Steiner point and a bunch of rays, indicating where we can merge with next. And it turns out terminal B, there's a suitable ray that goes to terminal B. So we can terminate, and boom, it creates an FST. So that's the basic idea. That's how FSTs are generated. So the important thing to note is that it's an iterative process. Every time you do a merge, you create a single 3 Steiner point, then you do it at every iteration and until you generate an FST. Okay, so that's all nice and good, but we only generate 3 Steiner points this way. But I've mentioned that we have 4 Steiner points when we have a restriction on the number of Steiner points. So, okay, so we have to create a new type of merge, and that is called the triple merge, because we're going to be merging 3 branches, and we're not going to go too much into the geometry, but the idea is you have 3 branches, each has a range of rays showing where it can merge, and if they are compatible, you can do what's known as a triple merge, generating a single 4 Steiner point, and again, you end up with a branch that has a range of rays. Yep. So on top of the double merge that existed for the k-Steiner algorithm, we add this additional triple merge to our algorithm so that we can also generate 4 Steiner points. So now we need to talk a little bit about why the k-Steiner algorithm is so efficient. So, I mentioned that the k-Steiner algorithm consists of two main phases, the generation phase and the concatenation phase. And in the concatenation phase, you're going to input a set of FSTs from which you're going to find an optimal solution. And the running time of the concatenation phase increases with the number of input FSTs. So you want to limit the number of FSTs that actually go into the concatenation phase. So what does the k-Steiner algorithm do? K-Steiner algorithm uses these pruning tests, which help you reduce the number of FSTs that actually go into the concatenation phase. And so remember I told you that in the generation process, it's an iterative process. So you do one merge at a time, generating a single Steiner point at a time. And what the pruning test does is at each step, it would verify whether it satisfies a certain property. And if it does, it would keep that branch. And if it doesn't, it can discard it because it cannot be part of an optimal solution. And this is very useful because this allows you to eliminate not a single FST, but you can actually, in fact, eliminate a whole family of FSTs during the generation phase. So the earlier you prune, generally the more impact it has. Okay, so the k-Steiner algorithm already has these degree 3 Steiner points and has a bunch of pruning tests that help you deal with these degree 3 Steiner points. But for our problem, we also need to deal with these degree 4 Steiner points. So one of our main aims was to introduce a set of pruning tests that help you deal with these degree 4 Steiner points. And I'll go through just probably the most fundamental pruning test that we've developed. So I'll do a little bit of explanation. So here you have a degree 4 Steiner point S, which is adjacent to its neighbors U, P, V, and Q. And let's say U and V are fixed. Then once U and V are fixed, you can calculate this point. So this point is the equilateral point of U and V, which means U, V, and this point is just it's an equilateral triangle. Then once you have this equilateral triangle, you can cut away a piece of that triangle using this ratio here. So you can calculate this region TUV and also this region TVU. And it turns out if the neighbors P and Q don't lie inside these regions TUV and TVU, then it cannot be part of an optimal solution. So how do we actually use this property during the merging process? It turns out when you have a triple merge, and like I know it was in the previous slide, it turns out that these vertices U and V, which are adjacent to the Steiner point, will become fixed when you do a triple merge. So because they become fixed, you can actually calculate these regions and then verify whether these other neighbors lie inside these regions. And if they're not, you can force them to be. And if they cannot be, then we can discard the branch. Okay. So that's the generation phase. So we've generated a bunch of FSTs, which contains at least the FSTs of at least one optimal solution. So then in the next phase, we have a bunch of FSTs, and then our aim is to find a subset of them, which together form the optimal solution. So how do we do this? We model the problem as an integer linear program, and we solve it using an RLP solver. So I won't go into details of that phase. Just to show the effects of the pruning tests. So I've ran two sets of experiments, one without the degree 4 pruning test and one with the degree 4 pruning test that we've developed. So I ran it for 5 terminals, 10 terminals, and 15 terminals. And didn't mention it, but k = 3, so you're allowed to have 3 Steiner points. And you can see that, so this is the running time of the algorithm, and you can see without the pruning test, you reduce the time taken dramatically, especially as you run larger instances. So I would say 1,000 to 3.3 seconds is quite a marked difference. And then again, in this table here, we show the number of FSTs with and without these pruning tests. So remember, I said that you want to reduce the number of FSTs to actually go into the concatenation phase. Well, with these pruning tests, you're reducing from 320,000 FSTs to down to 116. So it's making the algorithm a lot more efficient. Okay, so now we'll move on to the second problem. So again, we are given a set of terminals in the plane and terminals in the plane. We have some non-negative integer k, so a bound on the number of Steiner points. Then our aim is to find a connected network spanning n with at most k-Steiner points that minimizes the cost function. So it's the same problem, except this time we're choosing a different cost function. So instead of the sum of the length of its edges, we are now going to look at the length of the longest edge of a network. And this cost function is more suitable for wireless networks. So the problem, again, is NP-hard for general K. And there are no exact algorithms that can solve this problem in practice. So again, our aim was to make an algorithm which can solve this problem. Okay, so before we move on, so the cost function is only dependent on the length of the longest edge. So it turns out you can get optimal solutions that have things like cycles and other undesirable properties. So instead, we're going to focus our attention to a particular set of solutions. So in general, you'll have an infinite set of solutions, and our aim is to focus on the solutions which satisfy these certain properties. So we define a bottleneck k-Steiner tree, or a k-BST, to be a tree that satisfies these properties, which we'll go through. So in figure 25, I've given you an example of a k-BST. So we'll go through the properties together. So definition 1, T is a tree. So this graph is connected, and also it has no cycles, so it's a tree. We'll just go through point 3 first because it's easier. So every Steiner point has a degree of at least 2 and at most 4. And we have 4 Steiner points, S1, S2, S3, and S4. And they have degrees of 3, 3, 3, and 2. So that's satisfied. And now to check property 2. So every Steiner point lies at the center of the smallest disk containing its neighbors. So, and just to do that, we'll go on to the next slide. So, for example, we'll look at Steiner point S1. So the smallest disk containing its neighbors is just a circle that goes through its 3 neighbors, and S1 lies at the center of that circle. You can see that's the case for the other Steiner points. Even S4, which has degree 2, you can see that the smallest disk containing S3 and T7 is just this circle that goes through those 2 points, and S4 would lie at the center of the circle. So, which means in fact that S3, S4, and S4's T7 are the radii of this particular circle. So this gives you this nice property that these edge lengths become equal. So now with this nice property in mind, before that, we'll first define a minimum k-BST. So a k-BST that achieves the lowest cost function is called a minimum k-BST. And how come we can always focus our attention to this particular set of solutions? Because it's been previously shown that for any set of terminals n, we always have a minimum k-BST. So we can always focus our attention to these particular set of solutions that have this particular property. So we'll give a brief overview of our algorithm. So again, we have two main phases, the generation phase and the LP phase, which sounds familiar. So in the first stage, so we want to obtain a minimum KBST. So our aim is to generate a set of Steiner points, which contains the Steiner points of at least one minimum KBST. Then once we do that, in our second stage, our aim is to find a subset of those Steiner points which actually contain inside that minimum KBST. Then once you know the Steiner points of a minimum KBST, you know the entire vertex set of a minimum KBST, and you can just run a minimum spanning tree algorithm on those set of points, and it gives you an optimal solution. Okay, so remember the KBSTs satisfy those three properties that I mentioned before, and that allows us to divide the tree into these components, which are called cluster subtrees. And these cluster subtrees, denoted by these different colors, all have edge lengths that are equal. So for example, this, sorry, I should remove that mouse. This cluster subtree in black, so all of its 5 edges would have equal lengths. And you can see, you can have cases where these cluster subtrees can branch off the other cluster subtrees as well. So you can always divide in this manner. So now, so to generate a minimum KBST, we're going to generate these cluster subtrees that potentially belong to a minimum KBST. Then once we have those cluster subtrees, we can extract the Steiner points. So I'll give you an idea as to how the generation phase works. So first, we must obtain an upper bound on the edge length of a cluster subtree. And we can do that by running some heuristics. Then once we have a bound on the edge length of a cluster subtree, we'll do these merging processes, which sounds very similar to the other problem. So remember that for the other cost function, we had branches which had these rays indicating where we can merge and where we can't. But instead, for this problem, we have regions, which shows you whether you can merge these branches or not. So first things first, so we have what are known as these leading regions. So that will show us where we can merge and where we cannot merge. So let's say you have a neighbor of terminal T2. Then because we have an upper bound on the edge length of a cluster, any neighbor of T2 must lie within a disk of radius of the upper bound, right? So any neighbor of T2 must lie within a distance of that upper bound. And the same thing with T1. So the neighbor of T1 must lie within a distance of the upper bound from T1. It turns out that these leading regions have a non-empty intersection. So this means that we can merge these two branches together, because remember, this vertex must lie adjacent to T1 and also with T2. So it must lie within this intersecting region of the two regions. So we know this particular Steiner point is restricted to this intersection. Then the next vertex must lie within a distance of the upper bound from that region. So we can expand this region to R prime. So that will show where we can't merge for the next step. And we'll do this once more. So R prime is the region that we had on the previous slide here that shows where this vertex can lie. So again, we have an intersection with another region surrounding another terminal. And because we have an intersection, we can do another merge. So this vertex must lie in the intersection of the two regions R prime and R3. So again, it's an iterative process, but choosing a different cost function leads us to these different geometry, I guess. And it means that we have to do a merging process that's quite different from the previous algorithm. Okay, so again, we have these pruning tests. So I'll just go through an example of a pruning test. So every Steiner point must lie in the convex hull of its terminals. So I have a simple example of a minimum 1 BST. So this is the Steiner tree with one Steiner point that's minimizing the length of the longest edge. And its location is here. It will be the center of the circle going through these three vertices A, B, and C. And it lies in the convex hull of its terminals. If the pruning test is not satisfied, so if the Steiner point lies outside the convex hull of the terminals, it cannot be optimal, so we can prune this particular cluster subtree. And this is useful because we want to limit the number of Steiner points that goes on to the next phase to make the algorithm more efficient. Okay. So once you have that, so in the ILP phase, the next phase, our aim is to find a subset of the Steiner points that actually belong to a minimum KBST that are part of an optimal solution. And to do this, we use an ILP, but this time we use a different set of constraints. We use a flow formulation constraint to find this optimal subset of Steiner points. Okay, and yes, that means that we have a working algorithm that can solve a minimum bottleneck k-Steiner tree problem. So it's quite a mouthful. And you can see that it forms these nice clusters. So these edge lengths are all equal. These edge lengths are equal here. So you end up with the optimal solution that has a different geometric property compared to when you choose a different cost function. So that's my final slide. So just to summarize, we looked at the minimum k-Steiner tree problem for two different cost functions. And so our main work was done creating these algorithms. And then we spent a lot of time working on pruning tests specifically for the degree 4 Steiner points to make the algorithm more efficient when we run it in practice. Yep. So thank you.